Thank you. Thank you. Hello. This is my second RubyKaigi. I'm really happy to be here. A little bit about me. I go by Schneeman on the internet. One of the things that's really tied me and kept me committed to Ruby all of these years is actually literally being married to Ruby. This is my wife. Her name is Ruby. And recently she became a Python developer. So I make up for it though. I work for Roku. I started a open source project that was mentioned in the last presentation called CodeTriage.com. If you know anybody interested in getting involved in open source, CodeTriage.com will send you one open issue on an open repo. Say, for example, Bundler, if you wanted to get involved in that, or Rails. And also, I've been experimenting a little bit with documentation. And this is definitely in alpha, in beta. docsdoctor.org, it's kind of difficult to say, will send you one either documented method or undocumented method of your choice per day. So it's kind of a good way to get involved with a repo for documentation. And most recently, one of the things that I kind of accidentally, well, not really accidentally, I got involved with is a small conference in Austin, Texas. So Austin's our motto is keep Austin weird. So I love Ruby, and I think Ruby is definitely weird because it is optimizing for developer happiness. So we decided to throw a conference called Keep Ruby Weird. I am currently on the Rails issue team and just barely hovering in the top 50% or top 50 Rails contributors. And I want to talk about a little bit of my experience with a pull request that I had to Rails, and mostly we're going to be going over algorithms. So some more background about me. I attended school at Georgia Tech, and I studied mechanical engineering. I don't have a CS degree. And while I was at Georgia Tech, I just decided to pick up programming. I'm actually fairly happy with this. CS is very boring to me. I don't like lectures. I don't like, big O notation. It's very boring. But programming is very interesting. Building things that people actually use, that actually accomplish tasks. But having this self-taught programmer upbringing, I kind of was missing out on a lot of things that were traditionally brought by CS. And one of the big ones definitely is algorithms. So in general, like just through all my programming, algorithms are freaking beautiful. I love algorithms, and mostly not because of algorithms, but because of the problems that they solve. We have these standard problems that have been looked at for decades, and people can write them up into algorithms, share them, and improve upon them. So I have a big problem with spelling in general. I used to joke that it's a good thing I'm a programmer. It doesn't matter if I misspell the variable, as long as I consistently misspell it. But unfortunately, when you get tired or you get distracted, spelling becomes even harder. And when you're interacting with another program, spelling does matter. So if you're doing git commit and you misspell commit, then it might not work. But one of the really neat things is that Git will tell you, hey, like you totally added some extra M's to commit that do not exist. And so I ran into this one day when I was just super tired, and I was like, hey, that's really neat. Like, how does Git know that I actually wanted to like commit? Is there somebody in my program who's like looking at that and like, nope, I could fix that. So after a little bit of research, it turns out that the thing that Git uses is called edge distance. So edge distance is going to be the cost to change one word into another. And the less cost, the more likely that you have a match. For example, if we have two words, the cost of changing zat into bat is 1. It only takes 1 modification. The cost of changing zzat to bat takes 2. So it's pretty simple in practice, or in concept, but how do we actually go through and write the code for this was what I was curious about. So with basically no background and refusing to Google, I was like, I'm going to get this by myself. I decided to code up a very naive attempt, and it's super short. It's like, I don't know, a couple of lines long. Basically, we just loop through each character and check if the characters match. And I was like, oh, this is brilliant. I'll put in Zat, and it'll compare it with Bat, and it sees that, oh, the first characters don't match, but the rest of them do. The cost is 1. Like, solved. Done. Presentation's over. OK, so if that was the case, then I wouldn't be here. It wasn't perfect. If you put in longer or more difficult strings, then we would see that the cost it would return is just wrong. I mean, Saturday and Sunday are very similar words. It should not take 7 characters to modify these. So after this, I started to do a little bit of research, and I was like, OK, maybe Google knows a little bit more than I do. It turns out that the algorithm that I had written was very, very close, but not exactly Hamming distance. So Hamming distance is also known as the signal distance, and it is defined as the measurement of errors introduced in a string. One of the reasons that my algorithm is not the Hamming distance is that Hamming distance is only valid for strings of the same length. So Saturday and Sunday have different lengths, therefore it should have raised an error. But other than that, it was basically Hamming distance. Hamming distance is actually, turns out, really cool and really useful. The telecommunications industry uses it, especially on binary, basically, 1s and 0s. We can use Hamming distance to figure out if you need to error correct a certain sequence that was sent. But it turns out it's also really bad for misspelled words. Previously, if we wanted to change Saturday into Sunday, it should have only taken 3 changes, but instead it was saying 7. And the reason for that is Hamming distance, because we're only comparing individual characters, it only accounts for swapping characters, which is called substitution. It does not account for insertion or deletion. So digging deeper, we got into another algorithm called Levenshtein distance. I hope I'm saying that right. Anybody? Seeing some thumbs up, head nods, good. All right, people aren't entirely asleep. All right, so of those 2 things, we had insertion and deletion. We're going to take a look at deletion first. So if we're comparing two strings, here we have Schneems and Z Schneems. So it's pretty clear that we should be deleting the Z off of the second string. But another way to look at that is if we ignore the first character of the second string and only look at the remaining substring, do they match? If that's the case, then it turns out that you have a really good case for deletion, or that you should be deleting this character. A good way to calculate insertion is, it's kind of similar but the opposite. Here we have Schneems and, I don't know how to say Schneems without an S. I took a chance. OK, and so if you do the opposite, you actually only look at the substring of the first word minus the first character. And so this means that you have an insertion. All right. And then this will be true. So this equality will be true. Substitution, I know we already covered it, but it kind of makes the most sense of all of them. But when your first 2 characters just do not match, but the rest of them do, a good way to calculate that is knocking off the first character of both of your strings and seeing if the substrings compare. OK, with all of that combined, does that kind of make sense? Good. It took me a really long time to figure out why they were doing that and why that worked. Glad I hopefully explained that well. So overall, we can start to calculate distance by first pretending that we have a distance method. First, we want to calculate the distance between every single substring. So every potential change we can make. So this includes a deletion, an insertion, or a substitution. So again, pretending that we have a method called distance, we can pass it in two strings, str1 and str2, and it will calculate the cost for each of those. We then pull out the minimum value and add 1. Another thing that kind of confused me initially is like, why do you add 1? And 1 is to account for the actual operation itself. So by calculating the cost is only to figure out which operation you're going to take, and then adding 1 is to account for the actual operation. So you do that, you pick the cheapest operation, you add 1, and then you also have to account for whenever characters match. Previously, we covered this with knocking off the first character of your substrings. Again, so for example, Saturday and Sunday, the S match. So we no longer need to compare that character. We can just look at the rest of the word. And lastly, we have to worry about strings of different lengths. If you are comparing, say, foo and an empty string, then we've got 3 characters, or vice versa. You put all of that together, and whenever that happens, the string that is not empty is going to be the cost to change that. Whenever you put all of that together, you of course form not Voltron, but the recursive Levenshtein distance. So here's what it looks like. Those are the 3 pieces just put together, and if we can see that if I put in Saturday and Sunday, I actually get the correct response. So it's no longer just 7, which is really bad, and it actually looks a little bit like this. Okay, so anybody notice anything with that? Might have taken a little while to run. I did put a sleep in there just for dramatic effect, which is not in the official algorithm. So the one I did before, the almost hamming, I refer to it as dirty distance, took only 8 comparisons. We only had to loop through 8 times. Recursive took 1,647. That seems like pain. That seems like a lot. If we're going to have to, especially calculate a lot of different words, we need to have a better way of doing this. One of the interesting things, if you look at that enough, well, if you look at it enough, your eyes kind of glaze over. But if you keep on looking at it, you notice that a lot of those substrings appear on the screen multiple times. So we're doing the same calculations over and over and over and over again. So one of the things we can do is actually cache the intermediate values. We can cache the distance between substrings and make our algorithm much faster. And especially when you're dealing with things like spell checking, having a fast algorithm is really important. So to do this, we will be using a matrix, the Levenshtein matrix. Now, bear with me for a little bit. Some of this is just going to kind of be to prime you for actually how it works. But when we start off, consider for a moment, what would it cost to turn an empty string into Saturday? Well, turning an empty string into S would cost 1. That makes kind of sense. Into SA would cost 2, SAT 3, 4, 5, 6, 7, 8. So turning an empty string into Saturday would cost 8. Likewise, we can look at turning Sunday into an empty string. So how many operations would that take? You guessed it. It's very similar. It's 1, 2, 3, 4, 5, 6, 7. Stopped at 6. So this gives us our baseline. And this is how we are going to rationally think about changing one set of characters into the other. I took a look at this originally, and so it's also nice because we always initialize with just that set of 0 to the length of the string. Okay, so once we have that, that's just changing nothing, no string into something. How do we change our string into something? We look at it one character at a time. If you start out with the S, then just intuitively you can see, okay, S matches S, so it should be a 0. And you can keep on going and say, how do we change an S, which is on our left side, onto an SA? So that would be an insertion, and because we have to add the A to it, so that would cost 1. And that's generally how we'll go through this. But we need to have a way to do this programmatically. I'm not going to sit at my computer when anybody types in a git command and like physically look at it. That doesn't make sense. So in order to do this programmatically, we can actually pull on some of the logic that we used in our recursive algorithm. So we already said that this kind of makes sense. If we look at it and say the position, the character we're on string 1 represents the column, and the character we're on in string 2 represents the row, then this same logic is represented by looking at the matrix where at the row index and the previous column. So it looks a little something like this. Here's our row, here's our column, there's our column index -1, and then finally we want to add 1. So the total cost of that insertion would be 1. Does that seem kind of reasonable? Okay, all right. We want to keep on going, and in this case, all of the next of those are just going to be insertions because to change S into SA or S into SAT, we just have to keep on adding. So after this, we go down to our next line, and we'll be looking at SU. But we start over again. We want to change SU into S. Again, this is going to be a deletion. We want to just remove that U, and we can already do that kind of manually, but we want to be able to do that programmatically. We saw our deletion previously, and we can convert it into a matrix form exactly the same way. So in this case, we're going to be looking at the previous row. So we've got our column, we've got our row, and we look at the previous one. One way to consider this is by saying, all right, what if we deleted the U? What string would that leave? Well, that would leave S. So we would have the same cost of changing S into S as before, but then we also have to add 1 because of the action of deletion. So in this case, deleting would cost 1. So now we have insertion, we've got deletion, and we need to cover substitution. You guessed it, we run back through that same algorithm where we've got the row and the column. Our current column index is on the A, and the index -1 is on the S. The row is on the U, and -1 is on the S. And then we add 1 to also get a cost of 1. It just is super coincidental that all of these costs turned out to be 1. Anyway, so in the case of substitution, a way to rationalize it is saying, all right, if I was going to substitute U, I could substitute U for anything in the world. So it is basically guaranteed to match the next character. So therefore, it would be the cost of the previous substring, which would just be S, plus 1. And so that's how that works out. Of course, we covered match previously, but we didn't actually cover how to calculate it. This was our matrix, and essentially you just look at the diagonal. What was the cost of the previous substring? But you don't add 1. You just calculate the cost and propagate it. So basically, you're changing an empty string. The cost of changing an empty string to an empty string is the same as changing an S to an S because they match. OK, that was a little bit heady and a little bit wordy. If you didn't entirely follow me, I do have a set of a URL later on that you can actually play around with this. And when you put it all together, your algorithm's going to end up looking something kind of like this. And this is a modified algorithm, so it'll actually show you which action that it's taking. And you can see that it's using the exact same row plus or minus 1. It's a little bit converted just because this starts with a index of 0, and the algorithms previously started with an index of 1. But you can get the gist. When we do this, we iterate, and it'll end up looking a little bit something like this. Again, I slowed it down. It goes much faster. But we keep on going and going, calculating each value. And then you get your final cost, which is 3. One of the the coolest parts, if you are like super geeky and get really excited about geeky things, is that not only do we have the final cost, which is 3, we can also get the cost of all of the substrings in those 2 strings. So for instance, if you wanted to get the cost of converting Saturday or sun to sat, you just go to n and t, and where it intersects is the cost, because you've already calculated it. You don't have to calculate it again. So was this better than recursive? Yeah, all right. It took 48 iterations, which, if you ask me, is way better than 1,447. So again, I mentioned I do have this code online. You can go to github.com/schneems/goingthedistance. Or I also have a bit.ly link. Thank you, Ryan, for the recommendation. It is bit.ly/goingthedistance, and it's got all that code. You can run it from the command line. You can just step through it. I highly recommend going in there and modifying it and playing around. Also, all of my notes for this talk and my rationalization for why you're actually manipulating the strings that way are in the README. So please check it out. All right, so this was literally the basis of just what I wanted to do. Remember, I don't actually like computer science, and I don't actually like algorithms. I like solving problems. So the problem that I have, again, is probably spelling. And I'm human, and I get tired, and machines do not understand when I'm tired. So one day, I was trying to type Rails generate migration. But I accidentally typed something like Rails generate migratune. And then Rails was just like, no, that's not going to work. And then I was like, I'm going to flip this table over because I've been programming for like 12 hours today, and I had it with you, Rails. So one of the things that I try to focus on when I'm programming, especially frameworks and things that lots of programmers use, is thinking about stress. Stress increases whenever we try a really simple task and fail. Before I was implementing an OAuth provider, and it didn't quite work, and I was like, oh, a little bummed out. But I couldn't type Rails generate migration. I was so mad. And it's not because it's hard. It wasn't a difficult task. It was something that we all do. So was there a way that I could make it easier? Obviously, I'm like, oh wait, no. How do I spell migration? Was it with? What did I do? And I'm just like, man, I just want to copy and paste the word migration and be done with it. Why can't Rails be more like Git? And if they know what I'm doing, try to help me out. And then I was like, oh wait, Rails is open source, and I can add this. So I did. And this was pull request 15497. And you can see if you misspell a migration, then it'll actually recommend to you, hey, maybe did you mean this migration? And even if that's wrong, if it's not entirely correct, it'll give you the command to run Rails generate help. So whenever you type this, it catches the error. It compares the given command to any possible commands and iterates through all of them and recommends the one with the smallest distance. So using that algorithm. This is really similar to a company that has a product you might know. You may have used it. It's called Google. So Google will also recommend spelling for you. And I thought this, when I got on this spelling kick in Levenshtein, I lost half a day to this. I was like, this is so cool. How machines can know what's in my head and what I'm trying to do. So Google turns out that they do something very similar but slightly different. They actually just, I'm sure it's vastly, this is a vast simplification, but when they first got started, they essentially input a bunch of books. They said, all right, machine, you're going to read all these books and in English. And they categorized about 1 million words. After that, they counted all of the words. And they made the logical assumption that, all right, if a word shows up in here more times than another word, it's probably more common. So for an example is the word the, and, a are very, very common, whereas a word like quixotically might not ever show up in that text. So what they do is with that knowledge, they will then compare your input to the entire dictionary of words. And there are a couple performance optimizations, even more than the matrix method. You can store all of your comparisons in a trie, but I don't have time to go over that. and pull out the ones that have the highest probability, basically the most used, and the lowest edit distance. And then afterwards, Google shows you their suggestion. And this is where they get super sneaky. They make the suggestion a link. So if you click on the link, they're like, boom, this was exactly what you meant. And then they're going to cache that correct spelling suggestion so that next time somebody spells that exact same thing that exact same way, they don't even have to look it up. They just have it automatically. So this was my introduction into distance measurements and how I started to get excited about it. Like, I would love to see this in more places, like Thor, CLI. Have you written a CLI? Are you using options parse? Like, correct my spelling, please. In addition to Levenshtein distance, I also mentioned Hamming distance, but there's a ton more. Long and common subsequence. Manhattan distance is actually the calculating taxis. It's very similar to Google Maps, how that would work. Tree distance, and just a ton more. So even if you're if you are a CS graduate and fly that flag, instead of next time you need one of these algorithms, instead of just looking it up on Google and copying and pasting it, actually dig down and find out, hey, why does this thing work? Where are the roots of this? Where did it come from? And play around with it, share. Algorithms definitely are a way of sharing that institutionalized knowledge. And I mean, decades of research have come to the very moment where Rails tells me how to correctly spell migrations. It's a very beautiful thing. So please, I invite you to explore algorithms. I also invite you, I just learned this recently, thanks to Keiko. If you see me in the hallway, please give me a high touchy. It's like high five. And do we have time for questions? I think we have 2 minutes.
Does anyone have any questions?
Yes. So the question was, is there a gem version of Levenshtein distance? There is. It's actually a C extension, so it runs super fast. In my experience, you don't necessarily need that. You can actually copy and paste the algorithm from my pull request, or there's a copy already in Rails and another copy already in Ruby gems. It's a really common thing. Yeah, yes, there's a gem. That totally could have been my presentation. There's a gem for this. Drop the mic.
Hi. From what you know of pattern matching, would that have made the code of this algorithm clearer, or is it not up to the task? You had to write it from scratch the way you did.
Pattern matching? So, well, Google, if I understand your question correctly, Google actually gets into that, and you can start to do really cool things with n-grams, where you're hey, this word and this word and this word together. Normally, that's how Google does the like if you type in Taylor, they'll like autocomplete Swift, or maybe not, depending on you. But you can definitely get into that. This is probably just the easiest way to do a really simple spelling. If you're using Solar. Solar uses this tactic and just a giant dictionary of words that it can just like run through. Did that answer your question?
Not quite.
Okay.
Pattern matching the language features.
So I have no idea. That's a great question. If anybody knows, come and we'll powwow. Cool. Thank you very much for attending my presentation. Again, all the code, bit.ly/going the distance, or you can come find me. I also have Keep Ruby Weird stickers. Get them while they last. Thank you.
Thank you very much, Mr. Richard.